Alright, thank you so much for watching. In this video, we'll have a look at two different ways to solve the following problem. So find the smallest term of the sequence in which the nth term is given by the square root of n over 6 plus the square root of 96 over n, such that n is a natural number. And as always, I'd encourage you to pause the video, give the problem a shot, and see what you come up with. Alright, so let's get started here. First, what I'd like to do is look at the discrete variable n and switch it out for a continuous variable x, and have a look at the continuous function f of x is equal to x over 6, the square root of x over 6, plus the square root of 96 over x. And the thought here is that if you were to think about all of the terms of the sequence in the xy plane, okay, so if the terms are doing something like this, then f is a continuous function that will come through each one of those points. And if f has a minimum, and that minimum happens to be at a positive integer, then we'll have the n that we need that we know is going to give us the smallest term of the sequence. So first here, before I take the derivative of f to get the critical value, I'd like to rewrite it a bit as the square root of x over 6 plus 96 is 16 times 6, so the 16 can come out of the square root as a 4, leaving behind 6 over x. And this is nice because now I can make the following change of variable by letting t equal the square root of x over 6. And also notice that that would mean that 1 over t is equal to the square root of 6 over x. Now with that in mind, we can look at f of t, which is just the square root of x over 6, which is t, plus 4 times the square root of 6 over x, which is 1 over t, so t plus 4 over t. Okay, and now we can take the derivative of f of t, set that equal to 0, get the critical value, and see if it's a minimum. So f prime of t is equal to 1 minus 4 over t squared, and we want to set that equal to 0, which tells us that 4 over t squared is equal to 1, so t squared is equal to 4, which gives that t is equal to plus or minus 2. Now we'll run a quick second derivative test and find out if positive 2 is a minimum. So if f prime of t is equal to 1 minus 4t to the minus 2, then f double prime of t is equal to 8t to the minus 3, which is 8 over t cubed. So f double prime of 2 is equal to 8 over 2 cubed, which is 8 over 8, which is just equal to 1. So good. We have a critical value of t that turns out to be a minimum. So let's come back here to our original change of variable and get x. So square both sides, which tells us that t squared is equal to x over 6. And this tells us that x is equal to 6t squared. Now letting t equal to positive 2, we see that x equals 24. And this is exactly what we were hoping for. This value of x is a minimum of f of x, and it's also a positive integer, so it works for the n that we need. So we've established that the smallest term of the sequence in question is the 24th term. So we can finish off the problem by computing the 24th term, which is a24, which is equal to the square root of 24 over 6 plus 96 over 24. Okay, we're just putting 24 in for n. And that is equal to 24 over 6 is 4, so the square root of 4, plus 96 divided by 24 is also 4, so another square root of 4. So 2 plus 2 is 4. And there you have it. The smallest term of the sequence in question is 4. But, like I said at the start of the video, I do have one more way to solve this problem, and it's slick and quick, and I like it. So we'll start by recalling something called the arithmetic geometric mean inequality theorem, which tells us that for any list of non-negative real numbers, the arithmetic mean is always greater than or equal to the geometric mean. And in particular, what's going to be useful here is to just think of a list of two numbers. So what that would mean is that x plus y over 2, which is the arithmetic mean of two non-negative real numbers, is always greater than or equal to the geometric mean, which is the square root of their product, the square root of xy. And moreover, the theorem states that these two are equal, so the arithmetic mean of x and y equals the geometric mean of x and y if and only if x equals y. And that's going to turn out to be useful in solving this problem. So let's have a look. If we let x equal the first part of the nth term of this sequence, the square root of n over 6, and y equal the second part of the nth term of the sequence, square root of 96 over n. Now n is a natural number here, so everything's staying positive, so we can use the theorem. And let's start by looking at what the geometric mean of x and y are. So the geometric mean of the square root of n over 6 and the square root of n over 6 and the square root of 96 over n. So that's equal to the square root of their product. So that's equal to the square root of the square root of n over 6 times the square root of 96 over n. And this equals the square root of 96n over 6n. So the n's cancel here. 96 divided by 6 is 16. Square root of 16 is 4. Square root of 4 is 2. So look at that. Regardless of our choice of n, the geometric mean of these two terms is always going to be exactly equal to 2. And from the theorem, we know that the arithmetic mean of the two terms, which is the square root of n over 6 plus the square root of 96 over n divided by 2. So that's the arithmetic mean. And we've just shown that that's identically greater than 2. So for all n, that's greater than 2. And what this gives us is that the sequence itself, n over 6 plus the square root of 96 over n, the sequence itself is bounded below by 4. So that doesn't finish the problem yet, because it's bounded below by 4, but can it actually equal 4? And that comes down to the second part of the theorem. In order for the sequence to equal 4 at some n, the arithmetic mean of these two terms would have to equal the geometric mean. And that only happens when the two terms are equal. So setting the square root of n over 6 equal to the square root of 96 over n, we can square both sides to get that n over 6 is equal to 96 over n. Now let's multiply both sides by 6n to get n squared is equal to 6 times 96. And now n is equal to the square root of 6 times 96, We can bring the 16 out like before. So it's 4 times the square root of 6 times 6, which the square root of 6 times 6 is 6, times 4 is 24. So there you go. Just like we had before, the smallest term of the sequence is the 24th term, which is again going to equal 4. So I hope you liked the video. If you did, please don't forget to click like and have a great day.